Okay, so I ended off by saying that momentum is always conserved. So that is just something that you always need to keep in mind with these collision equations. So what you'll be given is an object. So they'll say you have one object here, okay, and you'll maybe have a second object moving along. Okay, and they'll give each object a mass. So let's see. So we'll give this object a mass of 3 kilograms, and let's give it a direction like that. And let's say it's going 3 meters per second. Actually, let's make the velocity different to the mass. Okay, and then the second object we'll give a mass of 2 kilograms. And they could ask several things. So one of the things they could do is they could say that the objects join up. And what is the final velocity? So let's say that this is at rest. They tell you that the second object is at rest. Well, that means that you know the velocity is 0 meters per second. Okay. So if they say at rest, you can infer the 0 meters per second. And what we know is that the momentum before, because momentum is conserved, that means momentum before so we say momentum, initial momentum is the same as the momentum after, so the final momentum. Okay, and as an equation, we could put it as so that the object here, so the momentum of the first object, so it'd be the momentum P of object 1 plus the P of the object of the second object, so P initial, momentum of the second, is going to equal the momentum of the two objects afterwards. So these are conserved. So they could tell you, well, these two objects joined together, what is their final momentum? What is the velocity that they travel? So what we would do is we would start by getting the initial momentum of the first. So that's 3 times 5, because P is equal to mv. P is equal to mv. And plus the momentum of the second object is going to be 2 times 0. Okay, and that's going to equal, so what if they join together? What we can do is we can think of them as one object. So now we've got a mass of them joined together, which is 3 plus 2. And so we can get their final velocity because we combine the masses and then we will know their velocity. I'm going to do the velocity in yellow for all of these. So V 5 0 5 0. And so the velocity we're not sure of, but it's V final. And so we know the V final is equal to 3 times 5 divided by 3 plus 2. And so we know that they go off at 3 meters per second. So that's the conservation of momentum in a nutshell. You have the initial momentum, which would be the objects at the beginning, and then the final momentum. And what they can do is they can, once they give you the velocities initially, then you can work out the final velocity. Now, they don't necessarily always join together. So what you could have is you could have them saying that the first object, the 3 kgs, slows down to 2 meters per second. What is the velocity of the second object? So I'm going to do a small pen and we'll just do that quickly. So again, we've already worked out the initial momentum. So P initial for that, where the second object is going off at, sorry, the first object we said slowed to 2 meters per second. Okay, so the initial momentum, P initial, I'm just going to put, because we've already worked that out, as 15. And that's going to be then the object, the first object slowed to 3. We're doing the velocities in yellow. 3 times 2. What is the speed of the second object? Well, we know the second object's mass was 2. And so we just need the V final of object 2. And so 2 times V final equals 15 minus 6. And so that would be 9 over 2. So V final equals 9 over 2, which is 4.5 meters per second. So we see what the second object will shoot off at 4.5 meters per second. And because it's the same sign, we know it's the same direction. Because momentum is a vector, we would need to assign directions to all of these. So we would just then say here to the right, and the same in this one to the right. Okay, so that's conservation of momentum. And the next thing I'm going to do is the elastic and inelastic collisions. So we see that what happened is these objects here can be different velocities depending on whether they get stuck together or whether one gets bounced off. And so because these velocities can have different values and directions, it means that at some point you could also get an elastic collision where kinetic energy is conserved. But we'll look at that in the next video.